Okay, so today we're going to discuss the residue theorem. Okay, now let C sub 0, let me write it, be an isolated point of the function f of z. Okay, now our goal is to determine the value of the integral f of z dz. Okay, now remember, if C sub 0 is an isolated point, that means it is inside the contour C. Okay, so this is our, let me write it here. C is a simple closed curve. Okay, simple closed curve surrounding C not, but enclosing no other singularities. So there's no other singularities inside our closed curve C. Okay. Now, we know that any function f of z can be expanded using Theorem 5, or rather the Lorentz series theorem, right? Now, let f of z be expanded in the Lorentz series. So we expand it about the point z is equal to z sub 0. Okay? So essentially, we converge that. So that converges, we need to make sure that it converges near the point that we are expanding our function in. So C equals C sub 0. Okay? Now, remember yung ating Cauchy's theorem. So recall Cauchy's theorem. We can get the integral of our B series, or in this case, we just take the B1 because that's where the rest that is our residue, right? There's a formula that I've shown before wherein we can solve for the values of the A, or the coefficients, the A sub n coefficients and B sub n coefficients. And do note that B sub n's are our coefficients for the what do you call this one? The principal part, meaning the negative powers of the power series. So B sub 1 dz over z minus c sub 0 is equal to B1 times the integral from 0 to 2 pi of rho I e I theta d theta over rho e theta, right? Now, if you look at this case, you can actually cancel out rho e I theta. Okay? Now, in this case, I is a constant, therefore our integration will just remain to be simple as d theta. So we're integrating d theta from 0 to 2 pi, right? Now, doing so, it is now as simple as b1 times I integral of d theta from 0 to 2 pi. And that integral is actually just equal to 2 pi, right? So this becomes b1I times 2 pi. Rearranging this becomes 2 pi I b1. Okay? Now, if we do have several singular points, right, or other b1s, right, we can actually write this, okay? So therefore, write it as the integral of f of z dz under or inside inside the closed simple curve C is just 2 pi I times b1, what we got here, right? Now, note that b sub 1 is actually our residue, okay? This is our residue of f of z. Now, if we have several residue, that is possible, okay? Because in this case, f of z has only one singular point, but it is also possible that you have several singular points, as we have seen from the examples of uh, taking or determining the Lorentz series, right? We did some examples wherein we have several points, like at least three singular points. Now, if there are more than that, more than, what do you call this one? More than one singular points, we can generalize that. So in general, the integral of f of z dz is 2 pi I times the residue of f of z at the singular point inside C. Okay? All right. Now, as I've said, if we have several singular points, so let me illustrate the first one, right? So the first one here is we only have a singular point inside our C, or the closed curve. So we can actually write that as, in this case, we have this particular closed curve. Let me, okay, if this is C, this is our C naught. So it's inside C. Now, in some cases, as I mentioned, we can have more than one, right? So what if we have something like this, and we do have several singular points, right? Now let me fix that. Okay, so we have, let's say, Z naught, we have C1, we have C2, and this is our C sub 0, C sub 1, C sub 2, and this is our general or the whole uh, closed curve. So again, remember, this is a counterclockwise integration. Now, what happens here, remember, is we can take a branch point for each, right? So that means we can connect those simple curves. So, and then approximate the radius of each smaller circles here to 0. And you doing that, we now include those singular points, right? So if we take branch points here, what's gonna happen is that, so remember, we are taking the integral counterclockwise, right? So we can take a branch point here. It's gonna go here. So taking the counterclockwise direction, but in this particular case, And then it's going to go back here and go through again in this case, right? Now, as you go here, you can also take another branch point to go to C1. And it's going to be this direction, going back to the main branch. It's going to go here, finally going through here, and go back to the original contour. And that's how it's done. Now, doing this kind of thing, we now include those 3 points uh, in our, or the valid point for our uh, f of z. Okay. Now, since you have several um, singularities, we can generalize the integral of f of z with more than one singular points to be 2 pi I times the sum of all residue of f of z. So if you calculate the residue, all the residue, okay, but then take the sum of those numbers and then multiply it by 2 pi I. Now, note that those residues should be inside C. Okay? Now, this means that we can simplify the integration. Okay? So this is what I meant when I said integrating without actually integrating. Okay? Now, of course, residue can be found using Lorentz series, right? If you expand it using Lorentz series, you can determine the value of the residue, as we have illustrated before. However, in many cases, it would be extremely difficult to determine the B1 or our residue, especially if we have a very complicated Lorentz series, right? So there must be a way of determining those residue without expanding the Lorentz series. But we can also do Lorentz series, right? So we're going to talk about the methods of finding residues. So basically, when we are doing integration in the residue theorem, we're not actually integrating. We are finding the residue, and then once we got the residues, we take the sum of them or sum of those values and then multiply it by 2 pi I. And that's it. That will be your answer. Okay. Now, the Lorentz series is much more tedious, but it's effective, right? Especially if the function is simple. Okay, so method 1 would be Lorentz series. So, for example, if we have f of z equals e raised to z over z minus 1. Okay, now the singular point here is 1, right? Because if we substitute 1 to z, it's going to give us an indeterminate or undefined value. So, find the residue. Find the residue at z equals 1. So we use capital R for the residue. So residue at 1. Okay. So how do we do that? Now, of course, we do Lorentz series. So we expand this power. Now, one thing that we can do to make this simple, look at the numerator. E raised to z over z minus 1 can actually be written as e times e raised to z minus 1 over z minus 1, right? In this way, when you multiply e back to e raised to z minus 1, it's just going to become e raised to z, which is the original one. Okay, now, once we have this, we can do the expansion for e, right? So the reason why we did, because maybe you're gonna ask, why didn't we expand e raised to z? All right, now if we do that, then we cannot divide or cancel out the denominator. So the denominator here is z minus 1. So the power series that we should get should be in terms of z minus 1. So this is the reason why we take we converted this into e raised to z minus 1. That way, our exponent for e and the denominator is going to be the same. Okay? So our power series is in terms of z minus 1, not z. Now, this is very simple. We already know the expansion for e raised to z minus 1, right? So the first term is 1, then plus the exponent, right? That's going to be z minus 1, then plus. So technically there's a over 1 factorial here, okay? Then we take the second power, c minus 1 squared over 2 factorial, and so on, right? Now doing this we have to multiply 1 over z minus 1, okay, to each of these terms inside, right? Now, our expression will now become e raised to z minus 1 times, so if we multiply it there, it's going to be, oh, I forgot, yeah, we have an e here, so multiplying that, okay, so we have e over z minus 1 times 1, so that's going to be e over z minus 1, then multiply to the second term, we're going to have, so plus, so z minus 1 will cancel out, so we have only e, then second we have plus e raised e times c minus 1 over 2 factorials 2, right? Now if we do multiply to the third term, the power of z minus 1 will just increase, right? So that means we no longer have any z minus 1 with negative powers. So now looking at here, remember the definition of our residue. It is the coefficient or the constant multiplying the z minus z naught raised to 1 or 1 power, which is actually this one. Now, if we write it in the form that we want, b1 over z minus z naught. In this case, b1 is e, c naught is just 1. So our residue is e, and that's it, right? But that's what I said, that it's kind of tedious if we use residue or Lorentz series. Okay. All right. Now let's talk about another method. Number 2. Two is what we call simple pole. Okay, so we defined simple pole before, right? So if our function f of z has a simple pole, so recall the definition of simple pole, okay? At z equals z sub 0 or c naught, we find the residue by multiplying f of z by z minus c naught and evaluating the result at c equals c sub 0. All right, let's use an example. Find R or the residue at 1/2 and R 5. So residue at rather negative 1/2 and R at 5 for this function. So f of z is equal to z over 2z plus 1 times 5 minus z. Now, the reason why we are asked to determine the residue at negative 1/2 and 5 is that if you look at, if you substitute negative 1/2 here, it's going to be 0. So that's a singular point. So basically, these are the singular points. Similarly, if we substitute 5 here, it's going to give us another 0 at the denominator. So both negative 1/2 and 5 are, both of them are singular points. Okay. All right. So let's do the instruction. So you cannot do this simultaneously, so you have to do it one by one. Okay. Now, remember, we multiply f of z by z minus c sub 0. Okay. Minus, that's very important. So the first one that we need is our z sub 0. Okay. So for the first residue, we have to take r of negative 1/2. So we substitute that. So z minus c sub 0, that is negative 1/2. So this is going to be z plus 1/2. Okay. And then we multiply it with f of z. So f of z is z over 2c plus 1 times 5 minus z. Okay. Now, we have to evaluate the result with z is equal to negative 1/2. That's what it. That's what this statement is talking about. Okay. Now, looking at the first expression, it's going to be z plus 1/2, right? So essentially, this is very similar to solving the limit of function, right? Because in some cases, it's gonna give us an undefined term, and what we want is to cancel out that term so that we don't have any 0 at the denominator. Now, if you look at z plus 1/2, it's actually very simple to cancel out because it's coming from the denominator 2z plus 1, right? Now, 2z plus 1, we can actually factor out 2, okay, inside or outside this one. And it's going to be like this. So times z. We can factor out 2. Then we're going to have z plus 1/2. Then we have 5 minus z here. Evaluated z negative 1/2. Now, if you look at here, we can now cancel this term. Then we are left with z over 2 times 5 minus z. And then we finally evaluate that for z equals negative 1/2. That's going to be negative 1/2 over 2 times 5 minus negative 1/2. Okay. Finally, we're going to have negative 1 over 22. And that is the residue for at z equals negative 1/2. Now, similarly, for R5, so z minus, again, so but 5 is positive, so we have z minus 5. Then multiply it to z over 2z plus 1 times 5 minus z. Then evaluated at z equals 5. Now, we have to cancel this term out, but if you look at the denominator, 5 minus z can be written as negative times 5 minus -1 times z minus 5, right? So we can have 2z plus 1 times -1 here. Then we have z minus 5. Okay, evaluated at z plus 5. So we can now cancel z minus 5. Okay, and we are left with, so we have a negative here, so we can put that above, so negative z over 2z plus 1 evaluated at z equals 5. Doing so, we have -5 over 10 plus 1. Then we have -5 over 11. All right, and that is how you find the residue using this method. Of course, this is only applicable for simple pole. Okay, now another example. So find r of 0, so the residue at 0, for f of z is equal to cosine z over z. So definitely, if you look at here, c sub 0 is 0. So if we substitute that to the denominator, it's going to be indeterminate, right? So using our method, r sub 0 or r of 0, so remember, it should be z minus c sub 0. But since c sub 0 is 0, it's just going to be z. Then multiply it with f of z. It's going to be cosine z over c. We can cancel out z. Then we have, so evaluate at z equals 0. We have cosine z evaluated at z equals 0. And cosine 0 is just 1. So that is the residue for this case. So writing it in a mathematical equation, r of z naught, or our singular point, simple pole, is just actually the limit of z minus z sub 0 times f of z as z approaches c sub 0. That is when c sub 0 is a simple pole. Okay, so that is for the second method. Now, there are many other examples, right? Now, since we're taking the limit, we can actually use L'Hopital's rule, right? Okay. So, let's use another example. Find the residue of cosine z or cotangent z at c equals 0. Okay. Now, we can simply use r of 0. So take the limit as z approaches 0. So c minus z sub 0 is just z. And cotangent is actually just cosine z over sine z. Now, if we substitute 0 for z, what's going to happen here? So what is sine of 0? Sine of 0 is 0. So we're going to have an indeterminate form. Okay. Now, we do remember that when we substitute 0, right? So if we look at, for example, we can isolate cosine 0, right? So cosine 0, and then the limit as z over sine z as z approaches 0. Remember, this is equal to 1. And remember in calculus, the limit of z or sine z over or sine x over x is just 1 as x approaches 0. So this is just going to be 1 times 1, right? So however, of course, what if you don't know uh, this kind of limit, right? So in this case, we can do some kind of analysis here. If you look at cosine and sine, they are actually connected with each other. One is the derivative of the other. Okay, so how do we do that, right? So we can actually take note that if f of z can be written as a quotient of two function g of z over h of z. So similar to this one, right? It's just cosine over sine, okay? Where g of z is analytic and not 0. So the numerator should not be 0, right? At z sub 0, that means only the denominator will give you the 0 term. And h of 0 or c sub 0 is equal to 0. So that one gives us the singular point, or the singularity rather. Then the limit or the residue for r or r of z sub 0 is the limit as z approaches c sub 0. Still do the same process, c minus c sub 0, but in this case, we have g of z over h of z. Okay. We can factor out, similar to what we did above. We have g of z naught, right? So we did that to cosine here, cosine 0. Now, the limit is going to be the limit z approaches z sub 0, 1 over, we're going to have to do the L'Hopital's rule, so h prime of z here. And evaluating that, we're going to left with c or g of z sub 0 over h prime, the first derivative, a of h prime evaluated at c sub 0. Okay, so that is for our, if we have this kind of situation wherein we can express it as a quotient of two functions. Okay, now we can generalize this rule. Okay, so r, hold on, r of c sub 0 is equal to g of z naught over h prime of z naught. We have some conditions. If the first one, f of z is equal to g of z over h of z, meaning we can express them as a quotient of two functions. And g of z sub 0 is finite, constant, and not equal to 0. So we cannot have 0 over 0. And finally, the h evaluated at z sub 0 is 0, and h prime, or the first derivative evaluated at z sub 0, is not 0. So that is how we solve this kind of problem. Okay. All right. So there are other examples. You may solve them. Okay. You can find those in BOAS and even in ARC10. All right, so that is for simple pole, right? So what if we have multiple poles? So that leads us to the next method. We have for multiple poles. Multiple poles. Okay, so ito yung similar to what we discussed. If we have a pole of order, so that means it's like z minus e sub 0 raised to n power. And the highest power is the order, right? So when f of z has a pole of order n, this is the method that we can use. Similar to the first one for simple pole, but it's going to be a bit more complicated. Multiply f of z by z minus c naught, but in this case, it's a power m, where m is an integer greater than or equal to the order of the pole, which is n, order n of the pole. And then, after multiplying, you differentiate. That means you take the derivative, the result, m minus 1 times, meaning it depends on it depends on the value of m. So if m is 2, then you just take the first derivative. If m is 3, then it's going to be second derivative, and so on. Okay? So differentiate the results m minus 1 times, divide by m minus 1 factorial, and evaluate the resulting expression at z equals c sub 0. Okay. All right, here we go. So let's use an example to illustrate this. Now we can actually write this in mathematical form. Okay. So r of z naught, let me write it below here. So first we multiply f of z by z minus c sub 0 raised to m. So we have z minus c sub 0 raised to m, multiply f of z. Okay, what else? Multiply where m is an integer greater than or equal to the order of the pole. Differentiate the result. Okay, so we'd have to take the derivative. So d, in this case, the derivative is m minus 1 over dz m minus 1. Okay, what else? Divide by m minus 1 factorial. Oh, we're gonna have to adjust. Hold on. Let me clear this one. Okay, so 1 over m minus 1 factorial. So what else? And then evaluate. So this is just r of c sub 0. And the result evaluated at z equals c sub 0. So this is the formula translation of that particular statements. Okay. All right. Let's use this in our example. So example, find the residue of f of z is equal to z sine z over z minus pi cube. All right. At the residue at z equals pi. Okay. So c equals pi will give us 0 denominator. So that is our singular point. Okay, now looking at z minus pi, right? Without the power 3, it's just a simple pole, right? But now we have power 3, so this is a pole of order 3. Okay, so let me write that here. So f of z as a pole of order 3 at z is equal to pi. Okay, let me clear this. Hold on. What's gonna happen here? Okay, here we go. All right, so let's use our formula. Now, my m should be less than or equal, right? So the pole order is 3, so it would make sense to use m to be equal to the order. In that case, m is 3, right? So if m is equal to 3, we now have r at pi is equal to 1 over 3 minus 1 factorial. Then the derivative is just 3 minus 1 dz 3 minus 1. And then we have z minus pi. Okay. C minus pi raised to m. That's going to be 3. Then multiplied by f of z. So our f of z is z times sine z over z minus pi cube. And we evaluated that at z equals pi. Now we chose m equals 3. Actually, the reason is to cancel this term. So because they now both have the same power, so we can cancel out, and therefore we eliminated the uh, the singular point. Okay. Now simplifying this, we have so 1 over 3 minus 1 factorial is 1 over 2 factorial. Now our derivative becomes second order. 3 minus 1 is 2. Then what we are left with is z times sine z, evaluated at z plus pi. Now taking the derivative, Remember, this is product rule, so you have z times sine c. But you do have to do twice the derivative, right? So we can do some scratch here. So d, you take first derivative first, and then we take the derivative of that. So we have d over dz of z sine z. Okay, what's the first derivative? So we take the first one as constant and the derivative of the other. So z times derivative of sine c is cosine z plus derivative of uh, z is 1, and then take that as a constant, right? So we have sine z. Now take the derivative of that. So d, just taking the derivative of the result. So we have z times negative sine c, derivative of cosine z, then plus derivative of z is 1, then we take cosine c as constant, and then we take the derivative of sine c here, it's just plus cosine z. Okay, sorry. So that's the final derivative that we want. So we can plug that back in. So r of pi is 1 over 2 factorial. So 1 over 2 factorial is just 1/2. Let's write it that way. Then the final answer that we need is negative z sine z. So we can add those cosines. So we have 2 cosine z evaluated at z equals pi. Now evaluating them at pi, we're gonna have 1/2. Oops, sorry. Okay, we have negative pi sine of pi plus 2 cosine pi. Okay, sine pi is 0, right? That is 180 degrees. So what we are left with is 1/2 2 cosine pi. So cosine pi is 1, right? So it's just be, oh, hold on. Did I miss something? No, sorry. Cosine pi should be -1. It's in the negative x-axis. So it should be 2 times -1, and we have -1. And that is the residue for that. Okay, so that is how you solve for the residue for multiple poles. Okay, now of course, the complexity of this method increase as we have more complicated expression. So for example, in the denominator, you can have more than, let's say, to the 6th power, so on, or you can actually have more than one pole. So for example, you can have z minus 1 here, right? Then what's going to happen there, right? So you can try to solve that kind of problem. Now, you do the same thing, actually. You process it because you still have multiple poles. So you treat this as the method of solving it as if it has a multiple pole. Okay? Okay, so there are several examples you can do. You can try to solve it in boas. Okay, so I think these are the only example. Maybe we can do one more. Hold on. Hmm. Yeah, no, it's just the same as what we had. So do some practice in BOAS, okay? Um, and then also I'm gonna give you the lecture for how to using residue theorem, solving the actual integrals. So far we only discuss how to solve an integral that involves a singular point. It could be a simple pole or multiple, and it shows that we only need to take the residue or sum of the residue and multiply them to 2 pi I. But remember that singular point should be inside your close or simple closed curve C. Otherwise, you don't include that. So you will see that later in some examples. Now, we also provided the method of solving for the residue because we need the residue, right? So we have the Lorentz series. It depends on the complexity. If you can solve for the Lorentz series, then you can directly get the value of the residue. Now, if you don't want that, you can also use the simple pole method and also the multiple pole, yeah, method. Okay, so that's it for today. So if you have any questions, feel free to ask me in class or email. Thank you so much and have a nice day.